welcome to my talk, File I/O, Past, Present, and Future. Thank you for choosing my talk over some really quite great talks that are happening at the same time. My name is... There we are. Oh, now I've got a big red spot. Dear. All right, then. My name is Guy Davidson. I'm the former head of engineering practice at Creative Assembly. Last year was a pretty dreadful year in the games industry, where I've been for most of my adult life, and I was not spared the ravages and the storms of headcount reduction that has swept through my industry. Has anyone here heard of Creative Assembly? A few of you, that's great. Anyone played Total War games? Yeah, yes, that's probably how you heard of Creative Assembly, isn't it? Okay. Yes, I started working on those in 1999. I'm on all of them. It was a privilege to work there, but you know, all good things come to an end. I was employee number 30 when I joined. I think we almost got to 1,000 people. I wrote my first game in 1980 on an Acorn Atom in Atom Basic. Anyone familiar with the Acorn Atom? 1, 2, 3. Yeah, come on, Charles. It's all right. You're amongst friends. It's fine. And I saved like mad to buy a ZX81, and I was 13 years old. And it retailed at £70, which meant it would cost about £340 or $430 or 400 euros today. But there were no euros in 1981. My parents were impressed with my industry and they helped me out. And I've been programming in C++ since the late 80s. I don't remember my first C++ program, but I was first paid to write C++ in 1992. I am a regular participant of ISO/IEC JTC1/SC22/WG21, the C++ Standards Committee. They all matter. All of these letters and numbers matter. They're a mechanism of distinguishing between all these people. That's the C++ committee, but I'm also the chair of BSI IST/5. This is the mirror group to the parent body of WG21, which is SC22, and this is the group that standardizes programming languages and system software interfaces. And I like to style myself as the king of programming since the UK is a monarchy. I started speaking at conferences in 2015, and now I tend to speak at 2 or 3 a year in addition to helping run them, and I also deliver training at conference workshops. Find me later if you believe that your organization could benefit from some training. Now, during the pandemic, I co-authored a book, Beautiful C++ with Kate Gregory. It's about the C++ core guidelines. Has anyone heard of the book? Has anyone bought the book? Has anyone read the book? Let the record show that everyone has bought and read the book. It has sold rather well, but your careers would be greatly boosted if you all bought at least 1 copy, maybe 2. Right now. I can wait, it's fine. This is a short talk. Sorry. The foreword's by Bjarne Stroustrup, and the afterword is by Herb Sutter. I was quite pleased about that. I'm working on another book, The Game Developer's Guide to Learning C++. Goodness only knows when it will see the light of day. I'm hoping for sort of summer, autumn next year, maybe winter, or 2027, I don't know. It's quite an undertaking. I don't know if you've noticed, C++ is a big, big, big old language now. The standard exceeds 2,000 pages. Anyway, the topic is File I/O, past, present, and future. I've broken the talk down into 5 questions. I'm going to take a sip of water, just 1 moment. So the first question is, why do we have files? What is a file system? Why should we avoid buffered file I/O? And how do we optimize unbuffered file I/O? And how might the standard help us in future? And I'm going to divide the talk into 5 orthogonal sections to reveal answers to these questions, okay? So it's sub-megabyte days, more RAM, more disk capacity, moving data into and out of RAM, file I/O in C++, from FStream to the OS SDK, and the 64-bit address space. And I would like a show of hands to see who wrote code in the 2010s, in the 2000s, in the 90s, in the 80s, 85, 84, ooh, 83, distinct lack of beards here, which surprises me, 82, 81, I've done this before with you, Charles, haven't I? Yeah, all right, okay. Charles actually wins. My first line of code was in 1980. Charles was in, I don't know, 1961? When was it? 78, all right, okay. Yeah, we've got a broad spread of people. I like the history of computing. We are losing it. Has anyone heard of Walter Brown? Walter Brown is a god amongst men, and if you come across any of his talks, you should go to his talks, because he's been there from a long, long time ago. And we need to know our history, because we need to prevent the mistakes that we've made in the past. So there is a fair amount of historical scene setting through this talk. I hope you find that engaging. I am a games developer, and Windows is my primary development platform, along with Visual Studio. I'm led to believe that there are some Linux developers here. No, it's all right, we're amongst friends, it's fine. Okay, yeah, cheers. Right on, brothers. Yeah. Using Clang and GCC, I presume. But the topics I'm going to cover should be OS agnostic. I will be detailing examples from the Windows SDK. It's what I know, but sort of down there, at the bottom of the stack, there's hardware that we're all familiar with. So please interrupt, ask awkward questions. Also be advised, I will leave time at the end for Q&A. I'm here until Saturday afternoon, so if you think of something in the night, hunt me down and I'll do my best to help. But please wait until the morning. Don't be scared to ask me to slow down, repeat myself, speak up, any of those things. I'm hoping the amplification is fine. We've got great audio here at this conference, I've noticed. But this is your conference, it's your talk for you to enjoy and benefit from. So, make sure I'm giving you the best. Okay? Everyone happy? Right, onwards. Before we answer the question, can anyone actually answer this question? Felix? Yeah. Ah, microphone time. John, run, young man, run to the front. Bring the staff of acoustic power. It's not the staff of acoustic power, it's the staff of muting. There we are.
Because at that time, so sometimes you need the data, even if the computer, later on when the computer would turn on again. But more important, the memory at that time was so limited that you could not have all the data in memory. So you had to somehow swap it or store it on disk.
That's a pretty thorough, good answer. Great, thank you. That's slightly awkward. All right, well, I'm going to do the next section of the talk anyway, despite Felix's excellent answer. Thank you for answering, because I do have, basically, if nobody answers, if nobody talks, it's about a 40-minute talk, so I need you to, okay, thank you. Right, who knows what this is? Yes, it is. ZX81, the cornerstone, the foundation of the revolution, really. So when I started programming, there was no storage attached to my motherboard, none at all. The CPU was a Z80, and it ran at a majestic 3 1/4 megahertz. Megahertz. That's 3 orders of magnitude less than this beast here. This machine boasted 1 kilobyte of RAM, 8 kilobytes of ROM, and that ROM contained a basic interpreter, a floating point calculator, and an operating system. 8 kilobytes, okay? It can be done. There were 2 ways of writing programs. You could either use the built-in basic interpreter and write quite simple things, or you could develop in Z80 assembly and really push the envelope a little. And after 3 months of basic, I wanted to push the envelope. I really, really did. I was completely entranced with the whole process. The workflow required me to use a program called an assembler, which would convert assembly instructions that I would type into a stream of bytes for the processor to consume. And the bytes would consist of code and any data required to run the program, which was usually a game, because that's what I was interested in. I was 14 years old. I didn't have an unlimited supply of 10-pence coins to shove in arcade machines. Now, this is the motherboard. On the left-hand side, you'll see three 3.5mm sockets. Yeah, you know what's coming, don't you? So one was for power. That's the one at the top. One was for input from a cassette tape. Who knows what a cassette tape is? Okay, I have to ask. All right, so who doesn't know what a cassette tape is? All right, who's never actually used a cassette tape in anger? You know, we're at that kind of age now. Well, I'm not, but you know, where you know, historically, data storage and all these sorts of things are just, they're just. I have never used paper tape. I'm sure you have, Francis. You don't surprise me in the slightest. Have you used a jacquard loom by any chance? So yes, one was for input, and the other was for outputs to the cassette tape. A cassette tape was, oh, I don't know, about the size of this adapter, maybe a little larger. And it was a long stream of magnetic tape on which ones and zeros would be recorded for future generations. So once I'd created this stream of bytes in my program, I would insert a blank tape into a cassette tape machine. Every home had a cassette tape machine back in 1981. And then I'd press record, and then I would tell the machine to output the byte stream to the tape interface. And similarly, I could load the byte stream back into the machine. But the important thing here was that there was one file. There was the entire program to be executed and the data to be used to run my game. It was all in one data stream. It was extraordinarily painful. The standard of the tape medium was variable. I can feel the PTSD emanating from. The standard of the player recorder, that was bad as well. And the control was out of reach of the machine itself. You know, when you say, oh, right, okay, write to file, please, the machine takes over. No. Back in these days, you'd say, write to file, and then you'd go over it and you press record on the device. You'd actually manually start recording, and then you could start the thing off. It was all hand control, but it's what we had. It was cheap. It was really cheap, and it worked. Now, this was my next machine, a ZX Spectrum. It wasn't much different. It had more color. It had more RAM, but still no machine-controllable offline storage. That happened there. It wasn't until my. That's. I did not run a floppy disk drive off my Spectrum. Congratulations. Wow. I must talk to you later about this. You can add to my talk. Right. You had one of these? Yeah, me too. I bought one of these in 1987, and it was my first exposure to files, you know, in what we understand as files. This machine came with a built-in 3.5-inch floppy disk drive and 520 kilobytes of RAM. 520? I could live in that. Virtual existence would be mine. It's the metaverse, all in there. We still haven't reached 1 megabyte, by the way. These are still sub-megabyte days. And it also came with a desktop. Come on, can I get this to work? Where's the cursor when you want it? There we are, right. A desktop. By Digital Research, in fact. And I suddenly needed to learn a lot more about programming GUIs. It was the first time I encountered a GUI. So 7 years of programming before I came up against files or GUIs. Graphic user interfaces. Do the kids still say that? Do we still say graphic user? Yes, Guy, we do. We still say graphic user interface. Thank you. All right. But my focus remained game development. I wasn't really interested in developing, you know, these kind of, you know, desktop software. And the offline storage really piqued my interest, because until this point, I'd simply created my games as a long stream of bytes, which the user would read into RAM before transferring execution to a known starting point. Now, the particular way this worked on the ST, the Atari ST, was interesting. You'd insert a floppy disk into the drive, and it would notify the OS that a disk had just been inserted. So the OS would read the first sector of the disk and then work out what to do. And if the sector contained the right byte combination, it would treat that sector as a bootstrap program and start executing. And this was how games would work. You wouldn't insert the disk and then open a window and then double-click on an icon or anything like that. You just insert the disk, and the OS would take over. And this had some rather severe security implications for the spread of viruses. It was no laughing matter, I can tell you. I trashed 2 Atari STs through poor disk hygiene. So yeah, security first, okay? Another interesting thing about the floppy disk was that it could store 720 kilobytes. And this was more data than the machine could contain, okay? Because there were 520 kilobytes on the machine, 720 kilobytes on a floppy. And at first I thought, wow, this means I can have more than one game on a disk. But as time went on, I realized I could do things like store multiple sound effects, extra graphics, or even different chunks of executable code specific to particular parts of any game I was writing. You know, I could just make my game bigger. And this is worth dwelling on briefly, because I simply decided to swap code in and out of a running process. This might be described as self-modifying code, which was certainly something I was doing a lot back in the early days on my assembly language on the ZX Spectrum. Anyone here written self-modifying code? Yes. Oh, don't be shy. Yeah, okay, great. No, it's great. It's fun. It's hilariously dangerous, but it's enormous fun. Because code is just a special kind of data, isn't it? You know, it's, and modifying code while it's running is just a special kind of transformation of data. But it's not so strange now. We've got DLLs in Windows. We've got, and you can load and unload those whilst you're running a process. Linux has got shared objects, I believe. Is it shared objects that you can, yeah, okay. I'm led to believe they're better. But then Linux people tell me everything's better in Linux land. But this is all rather safer and more controlled than what I was doing. You know, the idea of swapping code in and out it's embedded in the operating system, whereas I was just tramping over RAM, saying, hey, I'm going to execute this now. Anyway, here we are, moving data into RAM while a game is running. This is exciting stuff. How can I get it to move as quickly as possible? Now, there was an entire book, that book there. Does that work? Yeah, that book there. It was a couple of 100 pages long, and it was entirely devoted to the Atari SF354 floppy disk drive. Okay, a 200-page book on a disk drive. Okay, one of the advantages of the Atari ST was that it had extremely predictable hardware. Every Atari ST was made with the same disk drive. So I was able to completely understand the nature of the disk drive, how data was stored on it, and this enabled me to try such tricks as customizing the formatting of the disk, because normally the disk would be formatted MS-DOS style. So that was with 80 tracks, and each track would contain 9 sectors of 512 bytes. Who knows what MS-DOS is? I've just realized. Okay, that's fine. Yeah. If you don't understand anything, do stop me. I'm 56. I assume you all are as well, even though I can see that you aren't. But if you decided to write your own disk I/O software, then you could squeeze extra sectors into the outer tracks, because it's a disk, and the sectors get bigger and bigger as you go out. And you could also squeeze in extra tracks if you tried really hard. And you could customize the position of track 0 so that in the time it would take the read head to step to the next track, the disk would have spun to meet the next point. So you could create a spiral. I had so much fun just playing around with the disk drive. Like, it was an entire summer. At the end of which, I managed to create a spiral of data and read about 400 kilobytes from a 360 kilobyte floppy disk into RAM from inside track to outside track in 9 seconds. I never saw that. I'd never seen that kind of speed. I was so pleased with myself. I thought, I'm a programming deity, clearly. And all of this reading made me an extremely capable hacker and pirate as well. More on that later. Today, not in this talk. We're into 2-beer territory there. Now, a close look at what I'm describing here shows that only the medium has changed. I've exchanged a long strip of magnetic cassette tape, available from shops up and down the nation, for a series of concentric rings on a magnetic floppy disk. There is an improvement in that it's machine-controlled and the random access is more credible, which means that I can reasonably overwrite parts of RAM with other pieces of data from the disk while the game is running. But all of that's handled by me in my code with my slightly obsessive knowledge of the workings of the Atari floppy disk drive. And my knowledge of where in the stream of bits the pieces of data that I'm interested in lie. My workflow, however, was rather clunky. Every time I made a change to my program, I would have to reassemble the entire bit stream onto the disk. And this wasn't necessarily a problem, but it seemed that I could do better. Particularly, I wanted to be able to make changes to the bit stream on the disk while the game was running. Workflow, you see, you want to be able to save your work whilst the whole thing's in place. And that wasn't really possible. And it was at this point that I realized what files are. Okay, they're portions of the data stream on the disk. And file names are the bookmarks. And I moved over to using separate files for the executable and the data during development. And I could update them at runtime on my girlfriend's machine, because obviously I bought her an Atari ST for her birthday. Don't laugh, because I bought her an Atari ST for her birthday one year. She was pleased. She told me so. But yeah, for testing and experimentation purposes, having two Atari STs was great. I could make changes whilst the game was running, and then I could make changes on the other machine and then put them back. It's brilliant, it really was. And I introduced a retail build step, which would dispense with all the file searching, and it relied on my knowledge of the data, writing a single stream of data to the disk. And I was still developing games in assembly language, by the way. The Atari ST had a Motorola 68000 processor, so I'm still not into C or C++ or anything like that yet. Now, I like to separate the sections of my talks with art, artworks. Think of them as commercial breaks. And I also like to run quizzes. So I'm combining the two in one easy-to-swallow pill here. So I want the artist, the title, and the year. Who'd like to hazard a guess? Oh, really? Right. Mondrian. Okay. Would you like to speculate the title of the piece? It's it's probably his most famous piece. It's really banal. It's yes. It's composition 2 in red, blue, and yellow. No one's got that yet. Congratulations. Do you know what year he painted it?
Like one of our two
Okay. But do you know what year it was painted? There is a clue on the painting. If you look really, really closely, just there, it says PM 30. He painted it in 1930. And I chose Mondrian because Mondrian is an object-oriented version of the programming language Haskell. Who knew? Object-oriented Haskell, what the hell? And it's also a web-based code review system written in Python by Guido van Rossum. You all know who he is. It's whilst he was at Google. All right, onwards. More RAM, more disk capacity. I cheerfully carried on writing games and honing my skills throughout my maths degree, which I did in the late 80s at Sussex University. And I got my first hard disk, 44 megabytes in capacity, which changed how I did everything. Because my trusty Atari ST, hi. Yeah, you do, don't you? Nice beard. It cost me £285 in 1990. It was a big and significant investment, but it was totally worth it. It was absolutely worth it. I'm glad you asked me that, actually. That is relevant. You know, the way that my workflow was developing, I had a stack of floppy disk drives. By now, I'd upgraded to a 1.44 megabyte system, and I just had floppy disks lying everywhere. It was impossible to catalog them all. They were, and suddenly I thought, oh, I can have them all in one place. And now that I knew how files worked and what they were for, and like what filing was, and like filing cabinets, all of this files thing, because you know, at school, at university, you don't file things, you put them on the floor. You know, suddenly it became really important. It changed. My trusty Atari ST actually lasted until summer '91, when I was burgled. All my kit, and all my disks, and all my backups and everything, and it was a sad day. But my girlfriend had moved to a philosophy degree in the cognitive science faculty and bought a Macintosh, so I inherited her Atari ST. Good times. And I started again with the insurance money. But then I was burgled again about a year later and decided it was a cosmic hint that starting my own business as a game developer wasn't really my destiny. So I secured a freelance role as an interactive media company called UCM and started using Windows on PCs with enormous amounts of memory, sometimes as much as 16 megabytes. You could put a whole family on there, you know. I also came across Sound Blaster cards and Wolfenstein 3D, and by this time, PCs were coming as standard with hard disk drives. And games were being released on multiple floppy disks that took advantage of the excessive capacity available to them. And the idea of a single stream of data at retail became impossibly hard to manage, and some way of identifying and locating files became a necessity of development. Now, I had actually already been using file systems. I just hadn't been very conscious about it. They were simply mechanisms by which you would slow down the operation of your game, only of use when looking for the tools on your disks and loading them into memory. The disk format natively supported by the Atari OS was in fact FAT16, which was MS-DOS compatible. Now, disks that I prepared in my Atari were readable from any PC running MS-DOS, which, as far as I was concerned, was all of them, because back then they were in fact running Windows 3 on top of MS-DOS. But that's another talk. I love operating systems. This is an operating system talk. But does anyone remember what you had to type to start Windows from a DOS prompt? Win. What a great way to start your day. Win. What are you going to do today, guy? I'm going to win. I'm going to win at computing. Anyway, let's look at FAT16. It's actually short for File Allocation Table. We'll get to the number in a moment. It was originally developed in 1977. The file system uses an index table, which is stored on the disk, and that's the file allocation table. And it identifies chains of storage areas associated with the individual files. The table's immovable. It's allocated when the disk is formatted. You'll format the disk as, right, file allocation table is there, and the table is a linked list of entries. It's basically a tree on a disk. Each entry contains the number of the next cluster in the file, so it's like a tree of linked lists. The root directory of the disk contains the number of the first cluster of each file in that directory, and the operating system can then traverse the FAT, looking up the cluster number of each successive part of the disk file as a cluster chain until the end of the file is reached. If you've done, has anyone here written software before? Yeah. So, and have you done searching and sorting? Yeah. So it's exactly like that. Okay. So each entry in the FAT linked list is a fixed number of bits, 12, 16, or 32, hence FAT16, and the more modern, relatively modern, FAT32. The maximum size of a file is the product of the largest number that can be stored in the entries and the size of the disk cluster. And even if only 1 byte of storage is needed to extend a file, an entire cluster must be allocated to it, and any single cluster cannot hold more than a single file. So large clusters waste a lot of disk space if there are large numbers of small files. Please hold this thought. My custom format I was using for our Atari ST development was completely incompatible with MS-DOS. In fact, it was completely incompatible with Atari STs. It was a handy anti-piracy technique. Disk duplication was simply not an option. The only thing you could do was write a program to intercept the loader and then disassemble it, work out what on earth I was doing, and then replicate the writing software that I had written, which, no one's going to do that. There was a lot of reverse engineering. So FAT16 is a disk format, though, not a file system. We can look at that next. All right, who's heard of Posix? These are all easy questions. It's to lull you into a false insecurity of raising your hands and going, oh, yeah, I know. The Portable Operating System Interface, Posix, is a family of standards specified by the IEEE Computer Society for maintaining compatibility between operating systems. Posix defines both the system and the user-level application programming interfaces, APIs, along with command line shells and utility interfaces. For software compatibility, portability, with variants of Unix and other operating systems. Posix is also a trademark of the IEEE. Posix is intended to be used by both application and system developers. So remember I said I was a delegate to SC22? Posix falls within our purview. Part of the Posix specification is the file system, and for a file system to be compatible with Posix, it must implement strong consistency. For example, if a write happened before a read, the read must return the data written. It must have atomic writes, where a read either returns all data written by a concurrent write or none of the data, but is not an incomplete write. It must implement certain operations like random reads, writes, truncates, or fsync. It must control access to files using permissions and implement calls like chmod, chown, and so on to modify them. How does everyone say C-H-O-W-N, by the way? All right, who says chown and who says chown? Chown. Chown. I'm wrong, clearly. All right, then. I know, but it's chown. Like clown. I say GIF. I say GIF. So, right, off you go. Bye. Let's look at the C runtime library in this context. So we have file access, fopen, fclose, fflash. We have direct I/O, fread and fwrite, and we have unformatted I/O, fgets, fputs, getchar, putchar, formatted I/O, scanf and printf. And obviously we've now got libformat, Viktor Zverevich. If you see Viktor Zverevich, make sure you buy him plenty of beer, because he's given us an extraordinary improvement to the ergonomics of the standard library. And there is a scan coming up to match print, which I hope will make 26. We have file positioning, tell, seek, rewind. And we have operations on files, remove, rename. And when I first discovered the C file I/O library, there were two problems for me. First, how do I move bitmap data into RAM? Because I'm writing games. Secondly, how do I find files? And now when C was getting into its stride, the world of computers was text-based. So here's a fun fact. Oh, that's a color picture. Right, okay. In 1974, Evans and Sutherland released the first commercial frame buffer, costing about $15,000. 1974, $15,000. Okay, that's 3 houses back then. And it was capable of producing resolutions of up to 512 by 512 pixels in 8-bit grayscale. I know, be still my beating heart. Everything was text back then, when C was starting. Everything was text. Formatted input-output would insert values into strings. Unformatted input-output would put characters into a character array, and direct input-output would read n bytes into a void star buffer. And if we look at these APIs, you can see they all have something in common, a file star parameter, which we'll come to later. So how did I find files? I had to fall back on the operating system. One thing a file system should expose is an API for selecting files and enabling reading and writing. C does not have one of these, but since 2017, C++ does. I just want to stop and mention what a monumental task getting a stood file system into the standard was, and to honor the memory of Beeman Dawes, who died on December the 1st, 2020. And I want to quote Niall Douglas here. Beeman had an unusually large impact on C++ over his long and very productive life. My personal opinion of his most monumental achievement was getting file system into standard C++, which was probably the most tortuous, lengthy, and difficult library to have ever been standardized to date. And that followed a preceding, tortuous, lengthy, and difficult boost peer review involving multiple redesigns of the proposed library. Beeman was on WG21 from nearly the beginning, served as the library working group chair for some time, and was one of the original co-founders of the Boost C++ libraries. He also had a long history of continuous contributions to open source, starting from many of us were still children. And many of you weren't even born. He had periods of particularly poor health in his later years, yet kept up a work ethic which would shame most of us. He helped and advised me privately on a number of occasions, for which I was and still am immensely grateful. Beeman Dawes. Who's heard of Beeman Dawes? You've all heard of Beeman Dawes now. Let's talk about getting a proposal into the standard. It's hard work. The first thing you need to do is have a great idea and talk about it with your friends, with some experts, with plenty of people, and see if they think it's a good idea. And then you have to implement it. Okay, this is different from a proof of concept. You have to actually get the whole thing working. And if it's a library feature, the chances are you will already have been tinkering around with something in your spare time, or perhaps it's a library from your workplace code base, or it's something you saw on GitHub and thought this is an undiscovered gem. And if it's a language feature, things are a little harder. You need to implement the feature in an open source implementation of C++, and this can't be done for MSVC, which is one of the big 3 implementations. You have to fall back on Clang and GCC. Things can get sticky here because you might have a feature that works fine in those implementations but will fail terribly in MSVC because it can't be implemented. Perhaps the implementation forbids some handy private feature that you need to make use of. Once it is fully implemented, you need to socialize it. And this can be as simple as publishing a GitHub repo and counting the stars. And if a few hundred come your way, then it's likely to be a popular feature. This isn't so easy for new language features. Regular usage will generate feedback from users saying, hey, how about this? Or this doesn't work here in this case. And once the feedback is quietened down, you need to write the proposal with wording to be added to the standard. And this is the hard part, okay? You might need to get help from wording experts. And once you have a proposal, you can submit it to the relevant working group in the committee and let them chew it over. And this may mean flying to a meeting. Papers can be defended remotely, but being able to talk after hours with interested parties in person is invaluable. There will be extensive rounds of feedback and questions about the proposal, and the more preparatory work you can do, getting field experience and implementation experience on more than one implementation, the easier this part will be. Talking about it is really important. One thing I love about ACCU is that we actually do genuinely have a hallway track right behind us. Do talk to people, do reach out, just find out what each other's doing. It's the best part of this conference isn't the talks, not even mine. The best part of the talks, of the conference, is the people that you meet. Anyway, once the language or library evolution group has finished their review, it goes to the appropriate wording group to see if the wording will coexist with the existing standard. And whether it obeys the drafting rules. And they may have clarifying questions, and they may send the proposal back for design review if they're unhappy with the shape of it. And then once it passes the wording groups, it's voted on by the full committee meeting at the end of each session, the plenary. And even if it passes, others may write proposals to strike it from the working draft of the standard, and this happened with contracts, which you'll observe did not make it into C++20, although that was by group decision from the authors. It's a lot of work getting a standard in. It takes time and money, and a generous and understanding employer. It is not to be undertaken lightly. Taking up committee time on something you're not especially invested in means that the time doesn't go to someone who is invested in their proposal. And I've been working on a matrix proposal for some years now. I worked on a drawing proposal for a couple of years, only to have it set aside. Beeman's file system proposal had to straddle multiple operating systems, as well as C++ implementations. It was indeed a monumental achievement. Okay? Would that we could all work with his focus and diligence. Anyway, it had to handle files, file names, paths, all portably. And it's a great library for all of that. It's also a product of the time. It has twin error handling strategies, both error code and exception. And if you've been following the progress of std expected, then you'll know that there is a preferred way of handling errors now. Who's up with std expected? Yeah, good. Use it. So the library differentiates files between directories, links, block files, character files, sockets, and so on. And it accommodates special file names like dot and dot dot. And it has a full command of the vagaries of paths, including optional root names, as well as absolute, relative, and canonical paths. You can iterate through directories, find out how much space remains in your file system, modify file system permissions, and you can copy files, create directories, get file sizes, resize, and remove files. It's the kitchen sink. It's the whole shebang. But this is the file system, though, rather than the format of the file system on disk. And I remarked earlier that I started off using FAT16, which was MS-DOS compatible. The file system was defined by MS-DOS, while the disk format was defined by FAT16. And this separation is important because they often get mixed up. So let's look at this diagram. Anyone familiar with riser FS? Yeah, okay. It's a great piece of work, but unfortunately the developer is currently incarcerated. Now you can see that your application makes system calls to communicate to the Linux kernel. Everything below that, not your problem. Posix defines the behavior of these system calls. The VFS handles all the file system-related system calls, and this abstracts from the underlying file system. This means that if your file system developer suddenly becomes unavailable, you can simply swap for another one. Posix is great here. You can swap around file systems, and it doesn't matter. As long as there is a driver that the VFS can use to deal with the calls from Linux, all is good. And I should point out that Linux is only partially Posix compatible, by the way. As far as I can see, I did a lot of research for this, but I'm not a Linux user, so I might be talking nonsense here. But reads and writes are atomic on a page level. But a read might return some pages of a concurrent write operation, I'm led to believe. Do correct me if I'm wrong. It's worth noting that Posix was developed for local file systems as well. You know, all sorts of guarantees are available to you when you own a piece of hardware. You know, the thing is, Posix has been so fantastically successful that it has been the expected API for other file system solutions, including those whose contents are distributed over many devices. What we seem to want from distributed file systems are the presentation of the typical file system API, but with the opportunity to simply add more storage volumes as necessary. And many have tried. I went to Wikipedia, I looked at a comparison of distributed file systems. Many of them, particularly the proprietary ones, offer Posix as one of the access APIs. And I spent a chunk of 2022 giving talks about abstraction. And if you aren't familiar with the idea of abstraction, go and view one of them. I think the C++ on C talk is the best one. And the reason I remark on this is that I believe there's an abstraction problem going on here, because Posix abstracts the complexity of managing multiple processes, requesting I/O services from local storage. Distributed file systems require additional complexities to be abstracted. What happens when a device is temporarily unavailable, or when data takes much longer than expected to arrive in RAM? And when multiple processes on multiple machines want access to the same file, what happens then? That seems like a horrendous task to navigate. And I hope you can see that the word file system does a lot of heavy lifting. There's a lot going on there. One of the reasons that cloud computing has done so well is that it offers a better abstraction for the problem of distributed storage without pretending to be a general purpose file system. Anyway, that's file systems. I want the artist, the title, and the year. Have a guess at the artist. Come on, it's exactly who you think it is. It is Monet. Of course, Mathieu Rupert knows. One of your countrymen, I believe. Do you want to take a crack at the year? It's fine. I'm being jocular here. It's 1872. It's actually called Impression, Sunrise. And it's the painting that gave its name to the style and artistic movement. Impressionism. You all knew this. You all knew this. MonetDB is a database management system, and multi-wavelength optical networking, Monet, is a method of digital fiber optic communication. Right, moving data into and out of RAM. So now we have a way of finding our way to the bits on or within the storage device. How do we actually get that into RAM? So now's a good time to remind everyone how long things take. So I hope you're all familiar with cache levels. Levels 1 to 3 reside on the CPU. In another of my talks, I discuss how the whole of computing is about getting data to and from the CPU, really, and how data is stored in caches to speed up the transfer as necessary. Now, an Intel CPU made in the last 30 years will have a memory management unit on it. And this moves memory between RAM and the L3 cache. Now, conceptually, RAM is just another level of cache, really. It's just another storage place. It's data that's stored further away from the CPU. Is there another level? Well, there is, because data stored in storage devices like NVMe drives or SSD drives, any of those things, you know, that's another level of cache. All of these devices are connected to the motherboard, controlled by hardware local to the system. They store data even when the power is off. And the cost of this convenience is that it takes quite a while, relatively speaking, to move data to the CPU, because first it needs to move it to RAM, and that can take quite a while. And all of these devices are connected to the motherboard by a serial bus. And there is a world of difference between quoted bandwidth and what you will see in typical applications. So RAM comes in different bandwidths as well. That is the amount of data that can be read from or written to the RAM per second. But these variations are dwarfed by the growing disparity of speed between the CPU and memory outside the CPU chip, and this is known as the memory wall. And an important reason for this disparity is the limited communication bandwidth beyond chip boundaries. And this is known as the bandwidth wall. So between 1986 and 2000, CPU speed improved at an annual rate of 55%, Moore's law, while memory speed only improved at about 10%. So memory latency has become a significant bottleneck in computer performance. Who's familiar with big O notation? So big O notation made lots of sense when execution and data transfer took about the same time. But the disparity between that is enormous. We have to be a bit careful when we're throwing around big O notation calculations. But CPU speed improvements, they've hit a physical barrier as well. And Intel summarized this in 2005, which I shall read out again. So first of all, as chip geometries shrink and clock frequencies rise, the transistor leakage current increases, leading to excess power consumption and heat. Secondly, the advantages of higher clock speeds are in part negated by memory latency, since memory access times have not been able to keep pace with increasing clock frequencies. And third, for certain applications, traditional serial architectures are becoming less efficient as processors get faster due to the so-called von Neumann bottleneck, further undercutting any gains that frequency increases might otherwise buy. And in addition, partly due to limitations in the means of producing inductance within solid-state devices, resistance capacitance delays in signal transmission are growing as feature sizes shrink, imposing an additional bottleneck that frequency increases don't address. We've got a disparity between RAM speed and CPU speed, and it's getting broader and broader. And this has further implications for big O notation. That's another talk. But consider what goes on under the hood during a typical fopen, fread, fclose operation. So here's the fopen file signature. It will create a file object for you, and it uses that file object to hold a buffer to the file that you're opening. And how big is that buffer? Well, if you're on Linux, the macro buffsys will tell you. It's usually 4 kilobytes. And you can use the set vbuff function to change the buffer size if you're working with large files. When you call fread, the CRT, the C runtime library, will ask the kernel to read some data into memory owned by the kernel and then copy it to your file buffer. And from there, you can copy it wherever you like. Now, this seems a little suboptimal, copying it to a buffer and then copying it onwards. But consider what the rest of the API offers you. You can get individual characters, you can scan for runtime formatted data, and that's really useful, because what's actually happening is that the C runtime is caching data for you in the file buffer and maintaining pointers at the beginning and the end of the buffer, keeping track of where you are in the file itself, all of the bookkeeping. And also, the amount of time to perform that copy compared to the amount of time to move from storage into RAM is tiny, right? Well, it was. You might expect C++ to offer faster operations. Let's take a look. So now, instead of creating and managing a file object, we are managing a stream of data. We have the class fstream, which also has some really nice insertion and extraction operators, which you can see here match up with the get and put functions of the C file IO library. Last time I checked, and this was 15 years ago, but I don't see any reason for it to have changed, the MSVC fstream library was implemented in terms of the C file IO library. And there's a good reason for this. The C++ streams library was a product of the 80s. Okay, it's a great model of design for the period. It shows off multiple inheritance, virtual inheritance, good abstraction, an easier to use API. But it's still a product of an era where file sizes might exceed the available RAM of a machine. Okay, the important thing for a file IO API to do then was to move a cursor around a file and move chunks of the file into RAM. Database tables might contain millions of records, and whether they were on a tape or a disk, the job of the code is to read selected records into RAM and make decisions based on their content. So look at this struct. It models a record of a member of staff. Now, pop quiz, one of my favorite interview questions. How big is it? No hands shooting up this time. Yeah. Sorry? It depends, all right? That's the thing, it depends. And that's the bit that gets you into the next stage of the interview. It's where you don't try and guess a number, you start asking questions about the struct. So time t is an implementation-defined type, capable of representing times. Although not defined, this is almost always an integral value holding the number of seconds, not counting leap seconds. I fell foul of that once. Funny story. Awfully not funny story, actually. It's the number of seconds since midnight, January the 1st, 1970, UTC. It corresponds to Posix time. We're 54 years in. We're very close to 1.7 billion. So any guesses now? So can we agree on 84 bytes? 64 for the chars, 2 ints for the time, and 3 ints for the rest? Does that sound credible? Because no, because what I didn't tell you is it's 1974. And on this platform, an int is 16 bits, and a char is 7 bits, but stored in a single 8-byte value. Time t is a 32-bit value, because honestly, by 2038, we'll be using something different, or otherwise we'll have bigger problems to solve. I'm sure there's an XK, you know, there must be an XKCD comic about that somewhere. If it springs to anyone, do tell me. I'm not going to go searching through the archive. The giveaway here was ID high and ID low for staff members, because you don't need 18 quintillion staff members, which is what you'd have. You probably need more than 65,000, though, especially if you're the government. And also in 1974, people weren't on the payroll for more than 60,000 of anything, really. Anyway, it's 1974. The size of this struct is 74 bytes, and the code we need to read a record is this. So I want to read to my buffer, which is likely an array of staff member objects, 10 staff member objects from the file I opened a little while ago. This will also compile. Not only will it compile, it will also yield the required behavior. And that annoys me more than seems reasonable. And note I wrote size of staff member. This is future-proofing. If you recompile this today, int is larger, time t is larger. Who remembers the 2038 epoch bug? Okay, all right. Maybe I know more Linux than I realized. Okay. Known as the epocalypse. Oh. It started appearing in 2006, a few years after the Millennium bug. Who remembers the Millennium bug? Yeah, that's more like it. Okay, right, yeah. The problem was that Unix, and more particularly Posix, showed no sign of waning popularity, and after the horrors of the Millennium bug were avoided, the computing world swung its gaze to Unix time and decided that providing a solution 30 years ahead of time, rather than 3, was the right thing to do. One of the problems we have with our file.io API is that we have all sorts of places where we are tempted to encode the size of a thing as an integer, rather than calculate the size according to the supplied implementation. And this isn't restricted to reading data either. The corresponding write API is similarly trap-laden. We are extracting and inserting data with these operations. How does C++ help us write a better interface? Operator overloading comes to the rescue, and we have these beauties. And now that the type is embedded in the API, rather than some terrifying void pointer, we can write safer code. What do you call these operators, by the way? Okay, I'm obviously unusual in this regard. I'm a firm believer in naming them by what they are rather than what they do. So I call this a chevron operator, left and right. No one, okay. What about this? What do you call this? The parenthesis operator. Oh, you're laughing now, aren't you? I don't call it the function call operator. Your overload may not call a function, but that might be bad. What about this one? Subscript operator. These symbols are in fact brackets, not parentheses. I know people who name parentheses brackets, but I don't associate with them. But yeah, usually it's used for index or subscript. There's no requirement for that to be the case, though. I've heard this called the square operator. Naming is hard. I guess you have to do the things that you expect them to do. You don't want them to, yeah. Anyway, we have the chevron operators for inserting into and extracting from a stream of data. And this is delightful and safe and readable, and we can spool through a file in chunks according to the size of the buffer defined by the runtime, and safely read and write as needed. All is good. But looking under the hood, there's quite a lot of work going on, and I'm not going to do it here, but it's worth your time single-stepping your way through a function which actually calls one of these extraction or insertion operators, and see how much code is getting called, because you aren't reading a byte from a file, you're reading a byte into a buffer, which represents a window into the file. So there's bookkeeping to be done. What happens when you overrun the window? Your thread blocks while the kernel retrieves another buffer full of data. And it seems that we can do better than this. We're in the modern era with machines toting 16 gigabytes of RAM as standard. And this idea of carefully spoon-feeding files into RAM 4 kilobytes at a time is surely no longer appropriate. Why doesn't C++ offer any alternatives, like read the entire file into RAM right now, please? And the most obvious answer is that there are a world of machines out there deploying C++. This is an Arduino. Anyone here hacking around on Arduinos for fun? Yeah, it's great, isn't it? It's a lark. And who's heard of a freestanding implementation? Who knows what freestanding, yeah, okay, so freestanding implementations. People like me write software against an SDK, normally Win32, where the operating system provides lots of useful services. But embedded systems don't usually run with such fripperies. No operating system for them. They often have very limited amounts of RAM, back to, sometimes as little as half a megabyte, And the very idea of dynamic allocation is enough to send implementers into a frenzy of panic, to be perfectly honest. So in my day job, I rely on the Windows SDK to read large files into RAM, unbuffered and fast, rather than the C++ standard library. Right, artist, title, year. Oh, very good. The gentleman, for the record, the gentleman said DALI 2024. It's not, no. I'm gazing at Matthew again. Why on earth would art history interest you? It's Ingres, Jean-Auguste Dominique Ingres. Romulus' victory over Akron from 1812. It was painted in 1812. That obviously isn't 1812. That would be silly. So Ingres is obviously, there's the database. Did anybody ever use the Ingres database? No, it kind of sank without trace. There's also Ingres paper. It's a type of drawing paper that my friends tell me is really, really good, but I don't. I do music. I don't do painting. Right, let's review where we are with file I/O. We'll start at the top with fstream, which is described as implemented in terms of file style. I work on Windows for my day job, so this code would look like this. Let's go back a bit. Let's see what's going on here. So that's your C++ version. That's your C standard library version, which is also a C++ program, as we learned yesterday morning, to my embarrassment. And this is how you do it on Windows. fopen is implemented in terms of this on my implementation. So are we finished? Is that it? Are we all done now? And it's 3 o'clock. We've still got half an hour to go. Things are about to get a lot more interesting, to be honest. So remember I was talking about Intel and their processor. In 1982, Intel started work on the i386, releasing it in October 1985 as the 80386. And it represented a big step forward in the evolution of the x86 architecture. And I'm most interested in the inclusion of a memory management unit. The jump to 32-bit processing and the introduction of a virtual mode. Now, up to this point, the x86 architecture had worked with a segmented architecture. Anybody do any segmented architecture work? Oh, and you're not dead. Look at you. We few, we happy few, we band of brothers. I'm not. I did some work with it back in the 80s on 80286 machine, 90s on 80286 machines, the last of the 80286 machines. It's immensely frustrating. It's a topic for another talk.
It was great. Let's go back.
Who said that? Get him! Light the pitchforks! No, we're not doing it. We're not going back because the 386, look, the 386 added an on-chip memory management unit, and this paging translation unit made it much easier to implement operating systems that used virtual memory. We can have 32-bit address spaces. It's just easier now, really. Really? You're not going to agree with me, are you? It really is. Anyway, look, extending the architecture to 32 bits made it possible to address 4 gigabytes of memory without having to worry about segment offsets. Basically, in the before times, 16-bit architectures did this complex dance with pairs of registers to address anything beyond 64 kilobytes. And you'd have to... No, we're not going there. I'm not going to... Sorry? Huge pointers, near and far and huge pointers, and all sorts of... If you look at the Win32 SDK, it still says near and far in places. Anyway, look, the virtual mode made it possible to run one or more real mode programs in a protected environment. Running Windows on an 80286 processor meant starting your computer, running Windows by typing Win, and double-clicking on an icon to start a new executable. And if it crashed, the entire computer ground to a halt. So although it looked like an operating system with lots of programs running at once, if one of them failed, it was reboot time. Bad times. But running Windows on an 80386 processor in enhanced mode by typing Win/3 provided access to the virtual memory capabilities of the 386 family of the processors. So Windows applications could use more memory than is physically available. This is the Strahov Abbey Library in Prague, by the way. It's just a beautiful building, and I just wanted to include it because it's amazing, isn't it? Books, they're great. Don't forget about books. Right. It's an exciting phrase, more memory than is physically available. And it's done by swapping between RAM and external storage. So RAM that's not been accessed recently could be swapped into a hard drive. And the RAM left behind could be repurposed to another process. That's basically what's going on, all via the magic of an on-chip memory management unit. And a willing operating system as well. And rather than swapping individual bytes, though, the OS will swap pages of data. Rather than just doing 1 byte at a time, off, one back on, it clumps them into pages. And that page size is determined by the processor architecture. It's usually 4K, again, which is why buffs is 4K. And a system with a smaller page size would use more pages, requiring a page table to keep track of everything. All the bookkeeping takes up a lot more space. For example, if a 32-bit virtual address space is mapped onto 4K pages, it'll be 2 to the power 12. It's 2 to the power 12 times 2 to the power 20 is 2 to the power 32. But if the page, that's about 1 million. If the page is increased to 32K, that's 2 to the 15th power, so only about 100,000 pages are required. So you can muck around the page size to see if you need more, more or fewer pages. And this matters because since every access to memory must be mapped from virtual to physical address, then reading the page table every time can be quite costly. So a very fast kind of cache, the translation look-aside buffer, TLB, is often used. The TLB is quite small, and when it cannot satisfy a given request, that's called a TLB miss, then the page tables must be searched manually in hardware or software, depending on the architecture, for the correct mapping, and everything slows down terribly. Larger page sizes mean that a TLB cache of the same size can keep track of larger amounts of memory, which avoids the costly TLB misses. So you can see there's a balancing act going on here that has to be decided by the operating system implementers. Processes rarely fill up pages, so a lot of fragmentation will take place. Larger page sizes lead to more fragmentation unless you're managing the allocation of memory very carefully yourself. Individual pages can be marked by the operating system as being read-only or read-write or no execute or execute-only. That's really handy. It stops viruses from plonking memory in places. Or only accessible to certain categories of user. But now things get interesting because since we have a direct mapping between the TLB and physical RAM, we aren't actually limited by how much RAM we have, but how much total storage. On a 64-bit architecture, we have access to 16 exabytes of address space, which is far, far more RAM than you will ever find in a single machine in your lifetime, I'm pretty sure. That's going to come back to haunt me, isn't it? But it means it's possible to exhaust RAM quite easily. because as you add more processes to your operating environment, each of them will demand a few pages of address space. And when the page table is accounted for all of the RAM, modern processors can simply map the address space to other storage. The smart thing to do is to identify the least recently used page, move it to slower storage, and that frees up the page of RAM for the new demands. This is called swapping. We all know about swapping, I'm sure. If that page is required, the least recently used page is swapped out, and then that page is returned back to RAM. Let's walk through the diagram, okay? First of all, we have the CPU. It requests a virtual address either to write to or read from. No, I'm not. Oh, hello. There we are. I can see it here as well. And then we have the TLB, either holds it locally, up there, or in case of 2A, or if there's a TLB miss, it has to search the page table for it, in the case of 2B. And if there's a TLB miss, the TLB is updated. And next, that page is hit for data if it's in RAM, and if it isn't in RAM, then we suffer a segmentation fault. And the OS will intercept this segmentation fault and find out where on the secondary storage. There we are. Where on the secondary storage it stored that page. And then the page in storage is swapped for a page in RAM, up here. And the page table is updated. And this hammers your external storage. Configuring a partition on your fastest drive is the best way to make this happen. However, filling up your TLB will lead to dramatically reduced performance because we're looking for everything. So resist the temptation to keep allocating without regard for your operating environment, okay? And this conceptual blurring of RAM, I suppose, and external storage is quite interesting. I'll wait for Felix to take his photograph. There we are. There's more, because Windows programs, all programs contain several system DLLs or shared libraries in the process address space. And another thing you can do is map different process addresses to the same sectors. So you only need to load one copy of, well, on Windows, it would be nt.dll into RAM at any one time, and that can be shared between multiple processes. That's handy. It's being loaded read-only, so no process is going to change it. Indeed, no process is allowed to change it because one of the properties of the mapping process is whether or not the file is read-only. And we can take this a step further. We can map arbitrary files to arbitrary processes' address spaces. And this is a heavenly advance on the status quo ante, I can assure you, because rather than open a file and block while it's read to a kernel buffer, and the portion you're interested in is then copied to your buffer, you can simply map the file into your process space and access it as normal. And of course, first access to any page of the address space will still require a block as the data is read into RAM, but it's unbuffered, which means there are savings of RAM and memory copying. And not only that, but if you're in the habit of using only part of a file, for example, a file that has a header describing offsets to relevant parts, then only the relevant parts of the file will need to be read. You'll not need to carry out multiple read instructions, with all of the attendant bookkeeping. You simply access the addresses you are interested in and endure the blocking that you would have had to endure anyway. Also, you can map the file on one thread and read the file on another thread. You do this by touching addresses at 4 kilobyte intervals or whatever your page size is. And the moment you know that you're going to need a particular file, you can map it, instruct your touch thread to do the touching, and once you actually need to access the file, with any luck and sufficient advance warning, it'll already be there in memory waiting for you, and you'll suffer no blocks at all. This is incredibly important for people who play. All right, who here has played a video game? Who here has seen a loading screen? Yeah. Who wants to look at loading screens? No. This is a thing you can do. You map, as soon as you know a file, you start touching on another thread, do your processing, speeds things up beautifully.
It comes at a big price. It subtracts away from the space in Windows. So if you keep doing that, eventually Windows could even find itself out of memory because it can't map something contiguous anymore.
Absolutely. Once you've mapped something, it's a resource like any other, and you need to unmap it when you're finished with it. But that unmapping is I'm not counting that as file I/O, but you're quite right. That is that's absolutely what you must do. You can't just map you can't map your entire, external storage into memory. That won't work, sadly. The API is slightly more involved, just slightly more involved than the create file, read file pair. You'll notice that this is only 3 lines of code rather than the 4 required for the prior example, where you had to define your own buffer. There are a lot more parameters to worry about, lots and lots of them. I mentioned that I spent a while talking to conferences about abstraction. Here is abstraction writ large. The highest level of abstraction offered the simplest API. And as we delve deeper into the OS, things become more complex. Now, I'm making a massive assumption here, but I'm guessing that create file, read file on Windows works by mapping the file into the process and then copying it to the buffer of your specification. And without this buffer copy, we have unbuffered file I/O. The kernel delegates all of the bookkeeping to the memory management unit on the chip. That's why it's great. There's an additional problem, though, because modern processors have caches, instruction caches, data caches, level 1, 2, and 3 caches, all of which are copies of RAM. The value of caches is that accessing memory takes a long time. So when you address a piece of RAM, it's a smart move to simply get a big chunk of it and keep it handy for the next operation. Locality of reference, All of this is made possible by the memory management unit. It's an amazing thing. The assumption is that all changes to RAM are brokered by the unit. You need to be completely aware of all changes to RAM so that you can update the cache. Hold that thought. Who has heard of DMA? Great. I'll skip through this then because I'm rapidly running out of time. This is a thing we used to do ages ago, direct memory access. It enables you to tell a disk drive where to put data into RAM without bothering the CPU, except to notify the CPU when the transfer had finished. And it was an early kind of threaded I/O because it left the CPU free to carry on more important work rather than blocking on external hardware. But of course now all RAM updates are brokered by the on-chip memory management unit because of cache invalidation. So that's no longer available to us, although I suppose a read thread is a kind of DMA. There's an even better kind, which we'll come on to shortly. Right, easy one to close with. Artist, title, decade. Decade, mate.
15 something.
That would be 14 something. I'm going to say 1460s.
I'm really impressed. 1492 to 1498. We spent the 1490s, but honestly, you get below 1800, it's just a big blur for all of us, really, isn't it? Probably 1900's a big, 2000 is probably a big blur for a lot of us, Oh, that was in the last century. I know. I was asked, I was marking essays, and I was asked, can we make references from the last century? And I was going, yeah. Yes, of course you can. It's still relevant, Texas Instruments DaVinci is a system on a chip for digital video. The DaVinci Machine is a project to add dynamic language support to the Java virtual machine. DaVinci Project is a planned suborbital crewed spacecraft. And there is DaVinci, all uppercase, which is a NASA mission that sends atmospheric probe to Venus. All right, things have got proper huge now. Storage is huge. I can buy a couple of terabytes of NVMe storage for the price of a night out. 64 gigabytes of RAM will sit me back about the same amount. Files, on the other hand, have not grown at the same rate. At least not in my line of work. I really need to extract, I rarely need to extract portions of files, really, I just need to load textures or models or audio waves or video clips and I'm good to go. And why has C++ not caught up with this? So I want to close the talk by considering 3 potential arrivals coming to C++. The first of these is hash embed, P1040. Anyone heard of hash embed? Excellent, excellent. It started life as a proposal written by John Heedman-Ada for consideration by the C++ committee. The abstract is very simple. A proposal for a function that allows pulling resources at compile time into a program. What if I could store all my resources in the binary rather than externally in the file system? It's 1980 all over again. My heart leapt for joy. And I was quoted in the paper. So the first example looked like this. You can see what's going on there, can't you? That binary is a span of bytes. over a binary file. So the paper went round the houses in the C++ committee, but it didn't gain the necessary traction. One of the biggest problems was dependency scanning. But rather than grind through this issue, Jean Heed tried his hand in the C committee instead. That's exactly what he did. With proposal N3017, they do things differently in the rest of the standardization universe. They have N papers, in C++ we have P papers. We are the biggest programming committee, by the way, by a country mile. 250 people turned up in 2020 to Prague to verify C++20. Fortran is another language that is standardized. The last plenary had 12 people. Ada has 3. C++ is the 800-pound gorilla. It is the programming language. Rather than creating a library feature, the proposal is that hash embed be a preprocessor directive, like hash include, but for binary data. That's the way to think of it. It's hash include for binary data. And this was a popular position. The committee was mailed a physical letter of support from a senior engineer at DMG Mori in Japan. So, you know, it's a thing. So the example now looks like this. Of course, it's C, so there's no const exp. But it's easy to envisage a const exp value being used by a const exp function to perform compile-time computations that would have been performed at startup or during runtime. You're just shifting stuff left. Sorry. You're just shifting stuff left. Oh. This is the first time I've used this machine for presentations. It may be the last. Const exp all the things. There we are. So recall what I was doing back in the 80s. I would assemble a program full of code and data into a single bit stream and save it to a clunky external storage device. And then I would restore the entire stream to RAM. Embed allows me to relive those glory days from the comfort of my own machine. Particularly, okay, I want to talk about build pipelines. So this happens in multiple stages because engineers like me will write code. Particularly, we'll create text files full of code using our favorite tools like Visual Studio IDE or something like that. And these text files are our human outputs, our contribution towards the game. That code will be compiled into object files, linked into a binary, launched by the user, runs the game. Boom, jobs are good. But it doesn't stop there because it's not all about engineers. No, really, it's not. Other people, artists, people completely unlike me, frankly, will produce images and animations and sound effects and music and walls of expository text and all manner of stuff using their favorite tools. But their tools don't produce text files. Writers do. Writers produce text files. Everybody else produces binary files. And not only do they produce binary files, but those files are often in a completely unhelpful format containing information that we just don't need. Okay? Such as who authored the file, at what time, with what version of the authoring software. That's not relevant to the game. This is just header stuff. There might be all sorts of other information embedded in the file that we just don't care about. And rather than just ship this entirely and having the player, you know, pay the time penalty of filtering out all of that data while running the game, further increasing the amount of time the player spends looking at loading screens, there's an intermediate process for each of the different types of data which does all the filtering and produces a new file. And that is the file that can be optimally consumed by the game at runtime. And at my last company, we had a system called Bob, build on one button, where all of this would happen automatically. All the non-code would be fetched onto a single machine, all the various converters would be executed, and then the game would be compiled, and the binary created, and then a shipping image would be created using the converted non-code resource, and the binaries, and then everything would be ready for uploading to Steam. One button, brilliant. It was a purely automatic process. Every team should have one. Automation, it's really good, do it. But what if I could embed that data in the executable rather than having to use the file system? Because when you open a file, you need to parse a file name and let the file system do its work. Even if you decide to use an archiving system like zip, there's still parsing to do to locate the file. With embed, I can create my own file system which caters to the specific needs of the operation of the game. So locating files becomes a matter of dereferencing a pointer because I can use the C++ object model for all of my data. And we need a rather more involved patching story, but it does seem entirely worth it to me. Another cool trick we can do is parse the binary data for relevant information once only at build time, rather than every time the game is loaded. And this is it really is the very essence of shift left, doing things at build time rather than at runtime. Compile time parsing is something I'm really looking forward to exploring. I'm very grateful to John Heed for his work, I really am. Unfortunately, it isn't implemented in my compiler of choice yet, MSVC. So please contact your implementation vendors and request they bump the priority of implementing hash embed. It would make me very happy. And if you would like to read about how hard it was to get this blindingly obvious feature into the C standard, John Heed vents entertainingly at this address. MSVC users, anyone using Visual Studio? Good, no, great. So I've opened a developer community issue at this address, so you can go there and vote, and you can scan that QR code, and you can vote for embed. Now, I've got 10 minutes yet, come on. Vote now, vote early, vote often. I'll put all these links up at the end. Next, we'll take a look at a paper by Niall Douglas, gentleman who gave the encomium for Beeman doors. This is P1031. This is a huge beast of a paper, attempting to propose an entire low-level file I/O library to supersede I/O streams V2, if you like. It's a valuable paper in that it shows how much has changed since the I/O streams library was delivered to the programming public. Back then, spinning Rust was the name of the game. A randomly placed 4 kilobyte I/O to RAM takes up to 5 microseconds, while to a hard drive, using perpendicular magnetic recording, the time is more like 26,000 microseconds. So the usability cost of the I/O streams library was utterly dwarfed by the cost of the disk I/O operations. A SATA-connected flash drive takes maybe 800 microseconds, but it's also highly concurrent. It can service between 16 and 32 random 4 kilobyte I/Os in the same time it would take to service one. If you do the maths, every unnecessary memory copy increases I/O cost by a minimum of 20%. And if you take NVMe into consideration, we're looking at 300 microseconds rather than 800. And this is only going to improve, and the question to use buffered file I/O via I/O streams is going to become more costly. Anyone heard of Optane? The Intel Optane? Yeah. When that got killed, I thought, you idiots, really, it will rise. It will rise again. The paper, though, unfortunately, P1031, is way, way too large for the committee to review as a whole. So the way ahead is to break it into its constituent parts and introduce those instead. So next we'll take a look at P1883, stood file handle and stood mapped file handle. I'm sure you can guess what this is about if you've been paying attention to the talk thus far. In revision 2, Niall offers all the furniture required to standardize file mapping. So remember earlier I was talking about using the Windows SDK to optimize my file I/O. Okay. The obvious problem with that is that it is non-portable. If I'm writing for Windows, Xbox, and PlayStation, which I do, then I need to learn how each platform supports this feature, what each API looks like, its foibles, its functionalities, all of this malarkey. And this is exactly why standardization is a good and necessary thing. This is a CPU feature. It's not a GPU feature, it's a CPU feature, and it's part of the Posix standard as well as the Windows SDK. And I'm not going to tour through the proposal. It's 53 pages long. It's a well-written proposal. Niall's good at these. It's a cracking read, actually. It's still speculative, and it's beyond the scope of this talk, but I do recommend sitting down with a large pot of tea and studying it after you've digested his earlier paper. You'll learn a lot about file I/O. I certainly did, in general. And be ready for this feature when it finally lands. And if efficient file I/O concerns you as much as it concerns me, then you can do yourself a massive favor by contacting Niall with words of encouragement and support and asking how you might help. Even if this proposal doesn't form the basis of I/O streams V2, something does need to be done. I'm too busy with linear algebra at the moment. I'm doing matrix work, but I may swing my gaze that way. Now, one place the standard won't help us for a while is DMA, but Windows is giving it a good go with direct storage, and this works by migrating data across the PCI bus from an NVMe drive to a GPU card. Data doesn't transit through RAM, so the CPU is not bothered at all. At the moment, you need Windows 11 and a GeForce 3090, which rules it out for a lot of hobbyists, but as the cards start to support direct storage, expect to see game load times drop dramatically as the textures skip RAM and CPU time entirely. So we have files because a typical program cannot contain all the data it needs. Either there is insufficient RAM or insufficient address space, or there's too much data. Maybe the data isn't ready at compile time. It's supplied at runtime by the user or the machine. A file system is a way of organizing files such that they can be easily accessed via some identification system. Bits distributed across an SSD are organized by a file system that describes the start and end of a file. A file system is a series of bookmarks into the storage medium with handy search facilities. We should avoid buffered file I/O because it is expensive, and increasingly so, taking the whole amount of time required to move some data from an external storage medium to your program. The percentage of that which is simply moving memory from buffer to buffer is increasing as storage technology improves. We optimize unbuffered file I/O by using the information we have at hand. When we know we're going to need a file, we map it immediately. We start touching it on another thread. We're able to read the file if we need its data before our touch thread has reached that data, because it is mapped into the address space of the process. And the standard will help us in future by supplying a new version of IOStream and by eliminating the need for files in a few places via the new preprocessor directive #embed. Combined with constexpro, this will reduce runtime computation. Here are some useful links. Ask me 2 questions.